So before we can talk about the dual nature of electrons, we have to talk about light for a little bit. And so this overlaps definitely with physics. So light is a form of electromagnetic radiation. It's composed of perpendicular oscillating waves. One is the electric field and the other is the magnetic field. And we'll look at a picture in just a minute. An electric field is a region where an electrically charged particle is going to experience a force. A magnetic field is a region where a magnetized particle experiences a force. Something that's not magnetized does not experience a force. So if you have an ordinary kitchen magnet, it has a small magnetic field around it. And if you put it up to a piece of paper or a piece of wood, those objects are not magnetized. They do not experience any force. But if you put it next to another magnet, there will be a force experienced, whether attractive or repulsive. All electromagnetic radiation, all electromagnetic waves move through space at the same speed. That in and of itself is a little odd, but it all moves at the same speed and it's constant, and we call it the speed of light. That makes sense, right? Light moves at the speed of light. The speed of light is 3 times 10 to the 8th meters per second. So that's really, really fast, right? One of the things I love about watching cartoons with my kids is cartoons are notorious for breaking the laws of physics. I remember one really old cartoon where this old guy blows out the candle on the nightstand and then jumps in bed before the room gets dark, right? Is that possible? No. Light travels far too fast for that. So here's an illustration of electromagnetic radiation and the oscillating fields. So here we're showing the electric field oscillating up and down. So it's like a sine wave, and it's going up and down as it travels. So in this one, the arrow is this way. They're traveling this way. The magnetic field goes along with the electric field, but it's traveling in the horizontal. And so I can't do that with my hands. They're moving both at the same time in the same direction. Okay? So light travels at the speed of light. Sound travels more slowly. This explains the phenomenon of thunder and lightning. You see a lightning bolt hit something. You see the flash, and the sound comes later. The light got there at a speed of 3 times 10 to the 8th meters per second. Sound, more like 340 meters per second. That is much, much slower. And that is why you can time the distance. You can time it between seeing the lightning and hearing the thunder, and that'll give you an idea of how far away the storm is because of that difference. So we need to understand a little about these waves that are part of the electromagnetic radiation. So amplitude. Amplitude is how tall the wave is. So here is a wave, and the amplitude is how tall it is. That's the distance from the node where it passes 0 to a crest, or from a node to a trough. The node is just where it's passing 0. Amplitude measures light intensity, how bright it is. So larger amplitude, it's more bright. We actually don't use amplitude very much in chemistry. Another way of characterizing the wave is by its wavelength. This is given the symbol, the Greek letter lambda. It kind of looks like an upside down lowercase y. Lambda is the distance from one crest to the next, or from one trough to the next, or the distance between alternate nodes. So from here, skip one and go over there. It's how long the wave is. So here we have an illustration with 3 different waves, and they have different wavelengths. This is a long wavelength, a medium light wavelength, and a short wavelength. For light, what we observe when we see light of different wavelengths is we see different colors. So longer wavelength is going to be more of a red color, yellow's kind of in the middle, and blue and violet are at the shorter wavelength. So different colors for different wavelengths of light. The brightness has to do with the amplitude. Here, these two waves have the same wavelength, right? From here to here, it's the same. But this is going to be a very dim light, and this is going to be a bright light. Just difference in amplitude. Frequency is given the symbol nu. This is a Greek letter. It bears an unfortunate resemblance to a lowercase v. So you kind of have to watch out for that. The frequency is the number of waves that pass a point in a given amount of time. Number of waves is considered the number of cycles. And so a common unit for this is hertz. Hertz is cycles per second, or s raised to the -1 power. So cycles per second. So I think all of you, even if you've never been to the ocean, have at least seen the ocean on television, right? It's got big waves that come rolling in. And the waves have a frequency. Waves in water are, in some ways, similar to the waves of electromagnetic radiation. So if you stand knee-deep in the water in the ocean, and you count how many waves crash over you in, say, a minute or in 10 minutes, then you could come up with the frequency of the waves. You would take the number of waves and divide by the time that you're observing them in. The energy of waves is proportional to the amplitude and to the frequency. So if you think about standing, in the ocean, if the waves that are coming are very low, they're small, they have a small amplitude, or if they're very tall, maybe, they're like 8-foot waves, which one's more likely to knock you over? The tall ones, right? They're going to knock you over because they contain more energy. So higher amplitude, more energy. What about the frequency? Are you going to be more or less pounded if the waves are coming more frequently? You're going to get banged up more than if they're just coming every once in a while. So high frequency, more energy. Again, we have this thing here where we have high and low energy and frequency, and we have to remember how they go together. I find it difficult to keep pairs of things like that straight. And the way that works for me is to be able to think about it. So I imagine standing on the beach, well, which is going to cause me more pain? A whole bunch of waves coming quickly, or every once in a while? Well, the ones that come more frequently, higher frequency, are going to mess with me more, right? There's a lot more energy in that. So more energy, high frequency. Now, electromagnetic radiation all travels at the same speed, right? So the wavelength and the frequency are going to be related to each other because they're coming at the same speed. So the wavelength and the frequency are inversely proportional. If we know the wavelength, we can find the frequency because we know the velocity. The velocity is c, the speed of light. So if we think about this, I'm not very good at drawing these. So these are two crappy looking waves. I've tried to make them with the same amplitude. These are both traveling at the same speed. So this top one, is that lower wavelength, smaller wavelength, or higher wavelength, larger wavelength? The distance between, this is the wavelength right here. This is larger, right? So that's large wavelength, so big wavelength, and this one is small wavelength. So as these waves are traveling, which one is going to hit more frequently? The one with the small wavelength. Okay? So this one has the higher frequency, and this one has the shorter frequency, smaller frequency. So longer wavelength, lower frequency. Higher wavelength, higher frequency. No, shorter wavelength, higher frequency. Yeah, it's confusing. But we can calculate one if we have the other. The color of light is determined by its wavelength, or you could say it's determined by its frequency because they are related to each other. White light is a mixture of all the colors of visible light. It contains all the different wavelengths of light. When you pass white light through a prism, it separates the light by wavelength. As the light passes through this crystal, for lack of a better word, the light is bent differently based on what its wavelength is. It interacts differently with the crystal, and so it gets separated. And lots of different things can do this. Certain times of the year, I have little rainbows all over the entry of my house because there's this weird-looking crystal light fixture thing, right? And the sun hits it, and it makes all these rainbows. You can see a rainbow sometimes when the sprinklers are going, and you have little droplets, and there's a rainbow on your lawn. After a rain, sometimes we see a rainbow. And it's the same effect, but it's water droplets separating the light by its frequency or wavelength. It always happens in the same order. And so it's red, orange, yellow, green, blue, indigo, violet. One way to remember that order is Roy G. Biv. It'll be somebody's odd name. His first name's Roy, that's okay. Middle initial G, and his last name's a little odd, but whatever. Biv, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. This is why when children draw rainbows, a lot of times you're like, I can tell you're drawing a rainbow, but there's something wrong with it. It's because they've got the colors in the wrong order. You may not recognize that that's what's wrong, but your brain says, that's not quite right. When we see colors, okay, so like the lid of my cup here is this favorite color of mine, is pink, right? Or this girl's shirt is red. When we see colors like this, what's happening is the object is absorbing most of the wavelengths, and it's reflecting the one that we're observing. So it's reflecting, her shirt is reflecting red light. Her jeans are reflecting blue light. They're absorbing the others. When we see something that's white, it's reflecting all of the light. Something that's black is absorbing pretty much all of the light. And that's why if you go out go out to play baseball or something in the summer and you're wearing a black shirt, you're going to be a lot warmer than if you wear a white shirt, because your shirt is absorbing the light, and the light has energy in it. And so it warms up faster. Any questions about this? So we could do a calculation. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. So we need the relationship between wavelength and frequency. So frequency equals the speed of light divided by lambda, the wavelength. Well, what's the speed of light?
3.00
Yeah, in unison, awesome. 3.00 times 10 to the 8th meters per second. I'm not going to require that you memorize that. You do need to know that C stands for the speed of light. It says wavelength of 515 nanometers. So for this light, the wavelength is 515 nanometers. Okay, so this isn't too bad. We just put the numbers in here, right? 3.00 times 10 to the 8th meters per second divided by 515 nanometers. How are those units going to work out? They're not. Frequency should have units of per second. So we want the meter and the nanometer to cancel out. So we should convert our nanometers into meters. The simplest way to do this is just 515, instead of writing n for nano, write what it means. 10 to the minus 9 meters. That's not proper scientific notation. Your calculator doesn't care. So 515 times 10 to the minus 9 meters. Now the meters are going to cancel out. And we're going to end up with units of 1 over second. So I know that seems weird, but that's how it is. So we've got 3 EE8 divided by 515 EE minus 9 equals 3 sig figs. I'm getting 5.83 times 10 to the 14th. Anybody else get that? We could also say that that is 5.83 times 10 to the 14th hertz. Hertz is abbreviated Hz. It's a unit of frequency. It's not the rental car company. Any questions? You could also make this really big number here smaller by using metric prefixes. So hertz is something that you may have heard associated with your computer's processing speed, right? You know, a 250 gigahertz or, you know, kilohertz or whatever. It's the same unit here. It's things per second. So the electromagnetic spectrum is electromagnetic radiation, and we can line it up in terms of varying frequency or varying wavelength. It all travels at the same speed. Visible light is a teeny part of that. The shorter wavelength or the higher frequency light or radiation has higher energy. So think back to the ocean waves. High frequency, bang, 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 hitting you. That's more energy than 1 wave, 2 waves. That's low energy. So shorter wavelengths are high frequency. That's higher energy. On this spectrum, radio waves have the lowest energy and gamma rays have the highest energy. Gamma rays are this is the Greek letter gamma. Those are that's radiation with the highest energy. So high energy radiation can damage biological molecules. Anybody here gotten a sunburn? I think we've all gotten a sunburn at least once, right? What caused the sunburn? Ultraviolet light from the sun. Ultraviolet radiation. It's electromagnetic radiation. It has enough energy to damage your skin. Gamma radiation is way higher in energy. It's called ionizing radiation because as that high energy radiation enters a biological molecule, it can ionize things, and that's very, very damaging to living things. Okay, so here is the electromagnetic spectrum. So we can look at frequency, we can look at wavelength, we can look at energy. They are all related to each other. So here we have long wavelength and low frequency. Sorry. And as we go this way, the wavelength gets smaller and smaller, the frequency gets larger and larger. So a common misconception when looking at this is that the visible light here is going from here to here. It is not. It's just this little tiny piece right here. We're expanding it so that we can see it. We're more interested in visible light because we can literally see visible light. So visible light goes from about 750 nanometers to about 400 nanometers. Just this little tiny piece in here. Higher in energy is the ultraviolet. That's what gives you the sunburns. X-rays, that's what they use to look at your bones. Gamma rays, this is not good for you unless it's used very, very carefully. If we go to lower energy, there's infrared light. This is heat. Go lower than that, microwaves. Now you might think, well, microwaves make things hot in the microwave oven, right? And yeah, they do. But they're actually lower in energy even than visible light. How do they do that? Well, microwaves have a frequency that interacts specifically with water molecules and causes them to move more. It increases the kinetic energy of the water molecules, which raises the temperature. And so something with a high water content will heat better in the microwave than something with a very low water content. And then even lower than that are radio waves. So here's our very useful cell phone signals, FM and TV signals, and AM radio waves. I'm not going to go into any more details about these different types of radiation. You should read the section in your book. You should just be informed about them. Any questions?
When people try to say, when microwaves came out, like it was dangerous and all that, it's not really
no.
to the sun.
Yeah, people are freaked out about microwaves and, oh, I won't have a microwave in my house, or I've never eat food that's been microwaved, or don't stand in front of it. Yeah, it's just, there's an awful lot of crap out there. So as we saw earlier, a prism can be used to separate light according to its wavelength. White light gives us this beautiful rainbow. Infrared light. You recognize anybody in that picture? So this is my daughter Emily, and that's me. We went to the Jet Propulsion Lab, NASA's Jet Propulsion Lab, on a field trip. Very, very cool place. It's in Pasadena, or close to Pasadena. So they had this camera up. There's a picture in your book, but I just thought it would be a little more interesting, so I took a picture here. They've got an infrared camera and a regular camera, and so it shows you pictures on the monitor. And the infrared camera, instead of taking in visible light like most cameras in our eyes do, it's sensing infrared radiation. And the warm parts of your body, like our skin, give a different type of a frequency of radiation than the cooler spots, like our clothing, our hair. There's the background. It was very cool. And so it translates these into colors that we can see. Thermal imaging uses the infrared light. And this is, they sometimes have these things in helicopters, and so they can go out. It's also called night vision. So they can go out and search the area, and anything that's warm will show up. Well, if you're looking for a fugitive in the forest, he's probably going to be warmer than the things around him, right? And so you could see him in the dark. That's kind of cool. Gamma radiation can be used to help people. Have you heard of a gamma knife? A gamma knife is just a beam of gamma rays that can be used to cut tissue. Well, it's also damaging to the tissue around it, so it has to be used very carefully. But here's an example of how radiation that damages tissue can be used to get rid of, say, a cancer tumor. So you've got a tumor maybe in the middle of your brain. They can't go in and take it out. But if you take radiation beams from multiple directions and aim them at the tumor, there is some damage as this goes through healthy brain tissue. But you do it at a low enough level to minimize that. But it's all being focused on the tumor, and so the tumor gets lots of it and is much more significantly damaged than the healthy tissue around it. So, there's drawbacks to using the technique, but overall the benefits are better. So waves interact with each other, and that interaction is called interference. There's constructive interference, and there's destructive, that's something else, destructive interference. So if you have two waves that are in phase interacting with each other, they will add, and their amplitude will get larger. If you have waves that are out of phase, here this one's going up when that one's going down, if those are perfectly out of phase, they will add up to be nothing. Add up to zero. If you've ever jumped on a trampoline, This is the phenomenon that happens when you're bouncing with someone else and all of a sudden you just go like way higher than you should have gone. That's because you're getting some constructive interference from the other person's waves on the trampoline. Or sometimes you'll hit the trampoline and you just like don't bounce at all, and that's the destructive interference. Any questions? Another thing that waves do is diffraction. When waves travel and encounter an obstacle or an opening in a barrier, and the size of that opening is significant. It needs to be roughly the same size as the wavelength of the waves. They will bend around it. Traveling particles don't do this, but waves do. We see this, you can see this with waves in water, as well as things like light waves. So the diffraction of light through two slits separated by a distance similar to their wavelength gives us an interference pattern because the light bends and interferes. And this interference pattern is characteristic of all light waves. So this is what it looks like. So imagine that you've got these waves coming in, and these lines are representing the crests of the waves. So this is the top, and it goes down, and it comes back up. And so you've got this wave coming, and then it's hitting this slit. As it goes through the slit, it diffracts, it gets bent. And so the waves coming out are bent. Particles don't do this. If you have particles, they go in straight lines. If they hit the barrier, they're just going to bounce back or stop. If they hit the slit, they're just going to go straight through. It's not going to cause them to bend. But waves get bent. They diffract. Any questions? We can get this cool thing happening if we have two slits. So here we have a light source. Most light sources, like a light bulb or the sun, they're sending electromagnetic radiation out in all directions. So here's our source, and it's coming out from this source, and so it's going to hit this slit, and it's going to hit that slit, and at each slit it's going to be diffracted. These waves are in phase because they came from the same source. So as they interact with each other, we're going to get destructive interference and constructive interference. And so what we observe at some distance away is a pattern of light and dark spots. So it's bright here where we've got constructive interference and dark where there's destructive interference. Oh. Now we're going to watch another video that explains this. This is one of my favorite teaching videos.
What is light? What is light? What is light? That's a good question. What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras.
We all have auras.
Which are light?
Yes, they are. It lights up the room. It makes it not dark.
What's the difference between blue light and red light? The color.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right?
Yeah.
It would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes of small dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. What I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
Well, the obvious thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box, two bright bands.
Two little lines.
Yeah, I think it'll be one line for two.
I can expect to see the whole box lit up.
That'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No,
I see dots.
How many?
it's one circle.
Oh, there's one in the middle strongest, two either side.
The two on the outside are multicolored. The one in the middle is just white.
Kind of a rainbow.
The rainbow of colour as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. That's incredible.
So all we're doing is we're putting a light through two very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved there. The average person's not familiar with it. It's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light cancelling itself out.
This is basically the same as like having two drops of water fall in a swimming pool.
That's
You get exactly the same
And they go
pattern.
and overlap. As this ripple overlaps with those ripples,
Yeah.
down the bottom, you get a series of, you get like a bright spot, and then a dark spot, then a bright spot, then a dark spot, then a bright spot.
Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah,
That's
that's
because
working.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour difference is a different wavelength.
Exactly.
That's amazing.
So the difference
So
between
there's
red
still
and blue...
that red bin over there, the green part is just, I'm seeing
It's a
that,
different-
it's just different
different
wavelength. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, Ben.
Hey, thank you.
I have been enlightened. Literally.
any questions or comments? Yeah.
Is that why when the sun is setting, you see all the colors of the rainbow in the sky?
When the sun sets, what we're seeing is it's coming through more atmosphere than when it's high up. And that's what gives rise to the beautiful colors in the sunset. Yeah. Any other comments, questions? So what we saw with the ripples on the pond was this effect where as these ripples travel out, they're going to interfere with each other, sometimes adding and sometimes subtracting. And so wherever you choose to look at those, you're going to see a pattern of dark and light spots. Does that make a little more sense now? It's called a diffraction pattern. Okay, so jumping from that to the photoelectric effect. It was observed that many metals will emit electrons when a light shines on their surface. It's called the photoelectric effect. Photo for the light and electric for the electrons coming out. And classic wave theory said, well, that's happening because the energy from the light is being transferred to the electron. And when the electron soaks up enough energy, then it can be emitted from the metal. If this is our theory, then only the amplitude or the intensity of the light is going to affect whether or when the electrons are emitted. So just how bright the light is, doesn't matter what color it is. So this predicts that if you had a dim light, you would just need to shine it on the metal for a longer time before electrons were emitted. So there'd be this lag time. You shine the light, and at first nothing happens. And if you wait long enough, the electrons will absorb the energy and then begin to be ejected. Of course, that's not what they found. This is the sort of setup where you might measure something like this. So we have light striking this metal surface. The metal surface is inside, this is like a bell jar. It's an evacuated chamber. You need to get the air out of there because if the electrons hit the air molecules, then they're going to get absorbed by that and you're not going to be able to detect them. We have a positive terminal here, and so when the electrons are ejected by the light, they will fly towards the positive terminal and give us some current that's being conducted, and we can measure that. So the light hits, when electrons are ejected, we collect them and we can measure the current. So this is what they observed. If you look at different frequencies of light, so this would be low frequency, high frequency. As you change the frequency, nothing happens down here. Doesn't matter how bright the light is or how long you shine it on there, nothing happens. No electrons are ejected. When you get to this frequency, without lag time, bang, you're getting electrons being ejected. Past that, you're going to get electrons being ejected. But how far past you go doesn't matter. There's just this one place where, but lower frequency, nothing. Higher frequency, you get ejection. Now we see an impact from intensity. A higher intensity light is going to give you more electrons being ejected than the lower intensity light. So this kind of shot to heck the previous idea about what was going on here. So Einstein attempted to explain this. His explanation was that light energy is being delivered in packets. That light is not just a continuous wave, it's actually a stream of particles. Your book says it's lumpy. It's got chunks in it, it's got pieces. This is a little difficult to think about, but a packet or a piece of light is called a quantum or a photon. You've probably heard of photons. Ever watched Star Trek? Fire the photon torpedoes, right? Well, photons are packets of energy, packets of light. The energy of the photon, given the symbol E, is going to be directly proportional to its frequency. High frequency, high energy. And it's inversely proportional to the wavelength. So we can write equations like this. E equals h nu. So the energy of the photon equals a constant times the frequency. H is called Planck's constant, after the scientist, and the value is this. You don't need to memorize that. 6.626 times 10 to the minus 34 joule seconds. It's just a constant. Knowing that nu equals c over lambda, we can also write it this way. The energy of a photon equals hc over lambda. So longer wavelength is going to give us a lower energy. So we can calculate photons. We can calculate their energy. We can calculate how many are being emitted in a given period of time. So a 100-watt light bulb radiates energy at a rate of 100 joules per second. The watt is a power unit. Power is energy over time. So 100 watts is 100 joules of energy per second. If all the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? And we're just going to go with 3 sig figs in here. Well, yikes, right? Well, we've got a number here that we kind of recognize. 525 nanometers, that's the wavelength, right? That's the wavelength. What is the energy of a photon? What did we say over here? The energy of a photon is E times h nu, or E equals hc over lambda. We know what c is, and we know what lambda is for our problem. So we need this number, 6.626 times 10 to the minus 34. And that's joules per second. We know that C equals 3.00 times 10 to the 8th meters per second. So the energy of a photon equals hc over lambda. Well, let's put these together. H, 6.626 times 10 to the minus 34 joules per second times the speed of light, 3.00 times 10 to the 8th meters per second. And then in the denominator, is nanometers going to work there? No, we need meters. So we'll do that same thing we did in the previous problem. 525, instead of writing the prefix nano, I'm going to write what it means. 525 times 10 to the minus 9 meters. So how are these units going to work out? Well, I've got the meters are going to cancel out, right? Then I'm going to end up with joules per second squared. Did I do something wrong? I did something wrong. I got the units wrong on Planck's constant. It's joules times seconds. Yeah, so we got to fix that. This is wrong. Oops. So that was joules times seconds. And then down here, we got to fix it in there. Joules times seconds. Okay, now this is looking better, right? The seconds are going to cancel, and we're going to end up with joule, a unit of energy. That's better. Okay, so calculator. 6.626 EE minus 34 times 3 EE8 divided by 525 EE, oops, minus 9 equals. I've got 3 sig figs. So I've got 3.7863 times 10 to the minus 19 joules. What is that number? It's the energy of what? Of 1 photon. So that's the energy of 1 photon. So we could say it's that many joules per photon, right? Well, we're looking for how many photons are emitted per second. And then we've got this number, the power, 100 joules per second. So what we're going to do is we're going to put these things together so the units work out. So I've got my number here. There's different ways to approach this. I'm just going with what's coming into my head first. So this is, if I write this right side up, I'm going to end up with joules per photon, and that's not what I want. So start over here. Maybe let's start with the 100 joules per second first. 100 joules per second, because I want photons per second. So if I put joules in the denominator and photons in the numerator, then my units are going to work out. I learned dimensional analysis in high school physics class, the most useful thing I learned in all of high school. And the physics teacher said, you know, if you master dimensional analysis, you can fudge your way through much of physics. Because just put things together so the units work out, and chances are pretty good it's going to be okay. 1 photon for 3.7863, ran out of room, times 10 to the minus 19 joules. This is going to give me photons per second. So 100 times, this is going to give me an answer of, I'm going to round it now, 3.79 times 10 to the, no, I did that wrong. I was trying to be cute on my calculator, not a good idea. 100 divided by, I multiplied, that was dumb. 3.7863 EE minus 19. So I was getting less than 1 photon per second. That's just you do need to be able to do something like this. Arrange 3 colors of visible light. Here we're looking at green, red, and blue. In order of increasing wavelength, increasing frequency, increasing energy per photon. What do we do? Well, I'll show you how I remember stuff like this. And it's not by just memorizing it. I'm going to draw my own little electromagnetic spectrum, right? And so I remember Roy G. Biv. So red, orange, yellow, green, blue, indigo, violet. Past violet is ultraviolet, right? That's like superviolet. That's what gives you a sunburn. Is ultraviolet radiation higher in energy than visible light or lower? It can burn you. It's higher, right? So here's UV next to violet. This is high energy. And this then must be the low energy side. So if we're going in terms of energy per photon, which has the lowest energy? Red. And then green, and then blue. So in order of increasing means you start with the low one and you go to the big one. They apparently do not teach this in school these days. People have trouble with this. So red first. The red light is lower in energy than the green light. And the green light's lower in energy than the blue light. The blue light has the highest energy. Well, what about frequency and wavelength? I need to identify which end is high frequency, which end is high wavelength. So I think about water at the beach. It's a nice thing to think about. High energy would be waves crashing more frequently. So high energy is going to be high frequency. Low energy is low frequency. So the order for frequency is the same as the order for energy. Red, then green, then blue. And then frequency and wavelength have an inverse relationship. So the order for the wavelength is going to be opposite of that for frequency. Blue has the shorter wavelength, and green's is still in the middle, and red is the longer wavelength. Another way to think about this is not very scientific, but hey, it works. Which of those looks like it has more energy? The one on the bottom. This looks like a hyper little dog, right? And this is like some old hound dog that's like, right? Low energy, high energy. Look at this. This is a short wavelength. Short wavelength is with the high energy. So here's high energy, and there's the short wavelength. You have to figure out a way that makes sense for you to remember stuff like this. Any questions? Yes? The part with the picture? Letter C. Okay, so this is energy per photon. So I drew a little electromagnetic spectrum for myself. I know this order, Roy G. Biv. And so then I'm going to reason out which end is higher energy. So ultraviolet radiation gives me a sunburn. Look at me. I get sunburned if I just go outside and look at the sun, right? So very familiar with that. So the violet, and then there's ultraviolet. On the red end is the infrared. So UV's up here, UV's higher in energy. So I know that this end is high energy. The other end must be the low energy. And then I'm just going to look at this order. Red is on the low energy side, and then there's green, and then there's blue. So I've ordered them from low to high energy. Okay? Any other questions? Okay, we were talking about the photoelectric effect and how light energy would eject electrons. So one photon at that threshold frequency, the threshold frequency was this right here. So when we get to a particular frequency, this is called a threshold frequency, anything above that will get electrons being ejected. One photon at that threshold frequency has enough energy to dislodge a single electron. The Greek letter phi is the binding energy of the electron. So the electron is stuck to the metal with a certain amount of, it requires energy to pull it off. That's called the binding energy. If you put more energy, if you have a photon that's higher in energy, the electron is going to absorb more energy than is necessary to escape. So it's going to use that energy to escape, and then what happens to the extra electron? What happens to the extra energy? It becomes kinetic energy for the ejected electron. So I think of this a little bit like, say, going to Disneyland. So you send a kid to Disneyland, and maybe you give him $200. Disneyland's really expensive, right? And so maybe it costs $100 to get into Disneyland. Well, if you've got $200, you spend $100 to get in, what do you do with the other 100? You spend it on food and souvenirs and stuff, right? What if the kid has $100? Can they get into Disneyland? Yeah. They can get in. They can pay to get in. They can ride the rides and stuff, but they can't buy anything. What if the kid has $75? Are they going to let him in for 3/4 of a day? No, you don't get in. So there's this threshold. You have to have enough money to pay the entrance fee, right? So with the electrons, the photon has to have enough energy to pay the ejection fee. There's a certain amount of energy required to pull the electron off. If it's got more energy, then it's going to just shoot off faster. So the kinetic energy of the ejected electron equals the energy of the photon that comes in minus the energy that was binding it. So this gets spent at the door, and this is, and what's left is the kinetic energy. So it's h nu minus phi. Go home and say, hey, I learned that E equals h nu minus phi. You're going to go, what? So suppose a metal will eject electrons when struck by yellow light. What would happen if it was struck with ultraviolet light? So before we really look at these, we should identify in our minds, well, is ultraviolet light higher or lower in energy than yellow light? It's higher in energy. So we're saying if yellow light has enough energy to just kick them out, then what will ultraviolet light do? Would it cause no electrons to be ejected? No, that's not true because it's got more than enough energy. So that's not right. Electrons would be ejected and they would have the same kinetic energy as those ejected by yellow light. No. Are they going to have greater kinetic energy than those? Yeah. So the photon coming in, ultraviolet light, has more energy than needed. That's like the kid going to Disneyland with more than money to pay the ticket. So the extra money he gets to keep and do whatever he wants inside Disneyland. It's not possible to have the electron be ejected and have less kinetic energy than one ejected by yellow light, if yellow light is the threshold frequency. Any questions? So what we call the wave-particle duality of light is that sometimes light acts like a wave, sometimes it acts like a particle, and what behavior you observe depends on the experiment. When we do the diffraction slits, we see the wave behavior of light. When we look at the photoelectric effect, we see the particle nature of light.